Welcome back, everyone. I hope you had a wonderful short break. Is it my pleasure to announce the next lecture, which will be more of a tutorial or how to work with an actual toolkit, so you can do some visualization for yourself. Fun fact maybe is that I did all of my PhD in a toolkit called VTK, so it's a great honor for me to introduce our next speaker. We have Will Schroeder here from Kitware Inc. And Will was trained as a mechanical engineer with a bachelor from the University of Maryland and a Master of Science degree and PhD degree in applied mathematics from Rensselaer Polytechnic Institute. And after working for GE Power Systems and GE Research, he co-founded Kitware Inc. And Kitware was initially created to support the VTK visualization software toolkit, of which Will remains a core developer at this moment also, and has since grown to over 200 employees, with business and offices located worldwide, developing dozens of open source platforms supporting technology areas such as medical computing, computer vision, high performance computing and visualization, data and analytics, and software processes through its CMake build tool. Those are many words, but
yeah, thank you very much. That was great.
Welcome.
Yeah, so let me share my screen here. Whoop. Sorry about that. Let me share my screen. There we go. Well, thank you very much for having me, and thanks for that nice introduction. So I'm going to talk for about 45 minutes on the visualization toolkit VTK. I'll take questions along the way. So maybe every 5 or 10 minutes, we'll stop and just see if there's any chat questions or other questions that we need to address. So with that, why don't we get started? So first, I want to calibrate why we're here and why we're talking about VTK and the visualization toolkit. One of my first loves is in technology. It's just the whole broad field of visualization, and if you've been in computer graphics and visualization, you know it's a wonderful mix of both perceptual sort of soft science in terms of how humans relate to data, and then of course very rigorous scientific approaches to algorithms and techniques for mapping the data into perceptual forms that human beings can understand. So what VTK does is it basically bridges data and through a variety of mapping functions creates perceptual forms, typically graphics or animations that people can interact with. And it leverages the human perceptual system. And we all know how powerful that is. Just even in the day of machine learning, there's a very important role for human in the loop. Okay, so the visualization toolkit I'll get into it, but it's a very large system. And it covers a gamut of application areas ranging from medical imaging to computational fluid dynamics, to computer graphics, to simulation, to computational geometry, and so on. So getting your head around the system is very difficult, especially in a 45-minute presentation. But what we'll try and do is I'm going to go through some of the high-level concepts and hopefully give you a starting point so that if you start to use VTK, it might make sense a little faster than normal. So first of all, the visualization toolkit is what it is, a toolkit. And it's an object-oriented system developed in C++ primarily. Depending on how you count lines of code, we're talking anywhere from 5 million to a few million lines of code. So it's big. And one of the really very nice things about VTK is even though it's written in C++, there is a process for automatically wrapping those C++ classes into languages like Python, Java, and C#. So you can actually write almost any application in a language like Python that you can directly in C++. So a lot of people love Python and VTK, or Python and ParaView, which I'll talk about in a second, because you bring the strengths of things like Python and all the libraries, packages, and so on to along with VTK, and you can do some great work that way. VTK runs on most all modern computing platforms, Linux, Windows, Mac, and we've also pushed it onto mobile devices for certain customers. It's got, like I said, it has a wide variety of application area ranging from graphics, visualization, scientific and information visualization, computational geometry, image processing, volume rendering, and information analysis, mapping, and visualization. So the story behind VTK and how it started is actually very interesting. I was working at GE Research at the time, and because of the publication of the Object Modeling Toolkit, OMT, by some GE Research folks, the research center was really excited about people publishing books. So we decided to write a book on visualization, and we wanted to leverage what we had been practicing in a proprietary sense, and we wanted to share that with people around the world. So we adopted basically a BSD open source license in 1993, which at that time, was somewhat novel. I mean, not completely novel, but it wasn't like there was a ton of open source code available at that point. So anyway, we wrote this book. We wrote the software to go along with it. And it was mainly sort of demonstration, reference implementation software. It was slow, it was simple, it was limited in many ways, but we got it out there and people started using it pretty quickly. And the community, which I have a tremendous amount of gratitude for, basically started asking for features, improving the system, finding bugs and all that. And ever since that time, I've been a real, how do I say it, proponent of open source systems and open source application approaches. So one of my other loves in my current role is just working with the open source communities, whether it's VTK or other communities. And the book was published initially by Prentice Hall. Right now, Kitware has copyright to it, and it's completely open. You can get a PDF version of it, and the textbook's available in LaTeX or markup version. So if you go into the resource listing I'm going to show in a second, you can grab the book and just pull it down to your computer if you want to do that. So I said this earlier, but I'm just going to repeat it because it's really important. When you work with VTK, you need to think in terms of two approaches. If you're a developer and you want to develop fast algorithms or you want to develop novel algorithms, you're going to probably do that in C++. But once you do that, or you want to develop applications, you're probably going to want to use something like Python. So you have to have this sense of, if you want performance and core algorithm, C++, and if you want to do something else, you're going to use an interpreted language. And this is a very flexible way to get maximal performance as well as a lot of flexibility. Okay. Another thing that's worth noting is that VTK works in tandem with CMake, which I think many of you know about. It's basically a build tool that builds cross-platform. CMake is Kitware's most widely used tool. It probably has on the order of 5,000–6,000 downloads a day from our servers. It's also distributed as part of the Linux distros and so on. And CMake also works in combination with CTest and CDash for doing testing and web visualization of the testing process. And I only mention this because you really need to know something about CMake if you're going to use VTK's C++ code in combination with your own C++ code in order to build a system. And I also mention this is because VTK has had a philosophy from the beginning to basically make sure that the software is as stable and robust as possible. So we use what we call an integration dashboard or a continuous dashboard. And you can see on the right-hand side there, we basically run on dozens of platforms on a continual basis, ranging across operating systems, across compilers, across compiler options, across modules turned on and off and so on. And then the results of that testing is published on a daily basis, showing what's passing and what's failing and what the problems are. Ideally, the dashboard should be green. What you're looking at is a non-green dashboard, which generally we're not very happy with. But when you're building on so many platforms with so many developers, it's pretty common to have a state like this where you have some minor issues that you're constantly wrestling with. So we believe VTK is pretty robust and pretty stable, especially if you're using release versions. Okay. So, and just point out that VTK now is over 25 years old. It's very active. There's probably on the order of anywhere between 30 and 50 contributors in any given month. I thought when I started VTK that in 10 years it would be over. We'd move on to the next system, but here we are 25 or more years later, and we're still developing at a ferocious pace. And it's actually pretty amazing and gratifying because a lot of it's due to the community that's around VTK now. So this may be the most important slide in the presentation, which is where do you go if you want to learn VTK in a more detailed way? And I've underlined two areas. One is there's an extensive set of examples. I mean, literally in hundreds of examples, and they're well written and fairly well documented, and they're written in C++, Python, and I think there's some Java there. I haven't looked recently. So you can look at code and you can actually see how it functions, and you can download it and use it, and there's data to go along with it and so on. And then if you have any questions, there's a discourse forum that you can join and post questions there. There's Doxygen documentation. As I mentioned earlier, the textbook and user's guide are available and for you to pull down. So you can also look at that. And finally, before I go in sort of the details of VTK, I just want to mention that there are systems, applications like peer review, which are built on top of VTK. So peer review is an application. It uses VTK library to do some fancy visualization, and it adds a bunch of stuff on its own. For example, it does parallel data processing, distributed processing, and so on. It adds all sorts of animation plotting and so on. So in some ways, the easiest way to learn VTK is to start with something like peer review and start running with that. And then once you get the hang of what visualization is about and the visualization pipeline, then you can actually get into the bowels of VTK. And I often, when I develop, I'll do something in VTK, write out some data, look at it in peer review, fiddle with it, and then go back into VTK. So it's a natural way to go back and forth between the systems. It's very efficient. So I'm going to take a break there for a second. Are there any questions that we should address?
We do have some questions.
Okay, let's do that.
So the first question is by Yaroslav Agapov, and he asks, how's work on changing Rails from OpenGL to Vulkan going on?
What the question was, moving from OpenGL to Vulkan?
Mm-hmm.
Okay, great, yeah. So this is a really good question, and what we're thinking about doing right now is moving to WebGPU. WebGPU, in some sense, is a superset of Vulkan and Metal and some of these other renderings platforms. So we think that WebGPU may be the way to do it because it supports a variety of different rendering platforms, if you will, including the web. So we're probably 6 months to a year out from having a full-blown WebGPU implementation, but we already have one running, but it's a small subset of all the graphics capabilities that VTK needs to do its job. All right.
All right, thanks. There's one more question also from Yaroslav. It's Is there a way to easily plug VTK in your own rendering engine? He means use it as a kind of a library responsible for geometry, but control the rendering part.
Yes, that's done quite commonly. We find that people will just turn off the rendering part and just pick up the modules, the data modules and the filtering modules. And then just as the pipeline finishes execution, you grab the data and stuff it into your own rendering system. We also do things where sometimes VTK rendering and someone else's rendering are sort of talking back and forth and in harmony, but that's a little trickier because OpenGL is a very state-driven rendering subsystem. And if you don't get the states right, havoc can be wreaked. But yes, so the answer is, yeah, just use it as an engine for processing data. That's perfectly fine.
All right, thank you very much. There's no further questions at this time.
Okay, great, thank you. So I'm going to go through some concepts right now that will hopefully give you a better sense of what VTK is all about. And let's start at the top level, which is let me call it the visualization model. And it's fairly simple. It's basically, we have a bunch of classes, objects in VTK that represent data and different forms of data. I'll talk about that in a minute. And what they do is they represent data, they provide access to the data, and they compute information particular to that data. For example, derivatives, bounding box, things like that. So you have data objects, and then we have things that are called filters. And basically these things just take data in, they do something to it and spit data out. And finally, these data objects and algorithms or filters are combined into visualization pipelines. And what they do is just basically map data into perceptual forms. After the mapping, the data is sent to a rendering engine or written to file, or maybe sent to an AR, VR, virtual reality system, or whatever it is you want to do with the data. So from the perspective of the visualization model, it's pretty simple. This is what it might look like in an application. Basically, you have a sequence of algorithms or filters operating on data objects, and they generate geometry that are basically in the end rendered by the graphics engine or written to a file or whatever is appropriate. And so as the data pipeline executes, or the visualization pipeline executes, the data changes form. So you may read in something like a 3D volume, you might filter it with an isocontour filter that would produce a polygonal mesh, and that polygonal mesh may be mapped to the graphic system. So it's very common for the data form to change as it flows through the pipeline. I think this is obvious, but I'll make it clear. The algorithms typically have multiple inputs, multiple outputs, and sometimes we use the word source to refer to things that start the data pipeline. They might read a file, or they might be a procedural object that creates a sphere or something like that. A filter takes inputs and produces outputs, one or more inputs, one or more outputs, and a mapper will take one or more inputs and then produce a final mapping to the graphic system or other output form. So the way this is implemented is that we have this object-oriented hierarchy. The most abstract level is what we call data objects, which is just a field of, or I'm sorry, a blob of data, and it contains an instance of field data, and a field data is basically an array of arrays. It has no geometric or topological structure, and it is the base class or superclass of all VTK data objects. Now, one thing that's generally true about VTK is the data is represented by arrays. So it looks in some ways very Fortran-ish. Things are arrays, are not necessarily maps or more complex data structures. And we purposely did that early on because it turned out that when you're processing data and transmitting data and doing various operations on data, array structures are usually really fast. There are exceptions to that, and there's ways to iterate over data that may have, let's call it nonlinear, non-sequential forms. But generally, data in VTK is represented through a collection of what we call data arrays. So the derived class of data object is a data set, and it has some form of geometric and topological structure. And the model is quite simple. It's geometry, which are represented by points. So sort of fixing position in space, and then topology. Basically like a triangle has, is defined by 3 points and so on. And the data like scalars, vectors, tensors, or whatever, is associated either with points or with cells. So we call that point-centered or cell-centered data arrays. Okay. So this is what it looks like. Data object is an array of arrays implemented with field data. Data set has some sort of geometric and topological specification, and it has point and cell-centered arrays. And we call this stuff point data and cell data, and we refer to the data set as having points and cells. So pretty simple. So I think this is somewhat redundant, but I do want to mention that at the bottom of that slide, generally things are accessed via some sort of integer contiguous ID, integral ID. We call it a VTK cell type, or I'm sorry, VTK ID type. And a lot of times the structure or the information is represented either in an implicit form or explicit form. So what does that mean? So if I have a volume, which is say n, n by m by o in dimension, and I have its origin and I have its spacing between the voxels, everything is implicit, right? Because with the dimensions and with the spacing and with the origin, I can implicitly define a point of ID, ijk, whatever. So I don't need to represent or store explicitly information about the structure or about the topology. It's all implicit in the data structure. Something like an unstructured grid or call it a mesh, basically you have to represent every point with an XYZ, and you have to represent the topology by explicit connectivity arrays. Like a hexahedra has 4 IDs, 4-point IDs, or a tetrahedra has, hexahedra has 8-point IDs and a tetrahedra has 4-point IDs. So you get the idea. So there's this mix of implicit and explicit representations, and we do that to make sure to try and minimize the memory consumption by various data representations. These are common data representation types. Image data, rectilinear grid, polydata, which is rendered, goes to the graphic system, structured grids, and unstructured grids. And there are many more, actually. I've only shown a subset. There's probably another 5 or so different types that could be shown. Data sets, again, have attributes. This is point data, cell data, and we typically have data arrays to represent it, as I mentioned. And these data arrays can be labeled as scalars, vectors, tensors, normals, texture coordinates, and so on. And the pipeline is created by connecting together filters. And the way you do that is you basically invoke methods like set input connection and get output port that connects 2 things together. So the output of one filter is connected to the input of another filter. And sometimes you have more than one input or more than one output and so on. So I'm going to very quickly just describe the graphic subsystem. I've been talking about the visualization pipeline. So VTK has this thing called a render window, and the render window has within it a renderer. More than one renderer can exist in a render window. And the things that are actually shown are called VTK actors, or in some case, VTK prop. And the idea is it's lights, cameras, actors, right? That's the original metaphor. So we basically combine all these things: render window, renderer, actor, lights, for lighting the scene, camera for giving a viewpoint, mappers, which maps the pipeline, the visualization pipeline into the graphic system. And then there's some other things that I'm not going to really talk about, but there's things like transforms that can be used to position actors, scale actors, rotate actors, skew actors, and all sorts of stuff. And if you look at any one class like VTK camera, you'll see there's all sorts of methods for doing things like, elevation, roll, azimuth, changing direction of projection, changing view plane normal, doing roll, yaw, pitch, and so on. So there's an extensive set of methods that you can call on these various classes to control the rendering of the scene. So I'm just going to give you a very quick sense of what it might look like in a C++ application. So let's walk through it. What I'm basically doing is creating a sphere, a little pipeline that creates a sphere, and then rendering it. And if you look at the code, the first thing you'll see is there's a method called VTK new. And I'm not going to go into it, but objects in VTK are reference counted. So there's a reference counting mechanism to avoid duplicating data and keeping track of where it came from. And what the implications for this are important, because in some cases, like a bunch of points may be read from a file and it may actually flow through the pipeline without ever being copied. It's just shallow copied as it moves through the pipeline. So you're not taking extra memory as it moves through filter by filter. So that's what the VTK new stuff is about. It's a reference counting mechanism that you can look at, you can read about. So we create a sphere, we create a mapper. So we have a source and a mapper. That's a very short pipeline. The mapper is connected to an actor. The actor is basically associated with a renderer. The renderer is associated with a render window. There's an interactor that allows you to mouse over top of your object, and there's things like interaction style, so you can change the interaction behavior depending on what you want to do. And then there's things, if you look down below, renderer, you can set the background color, you can set the size in pixels, you can render it, and then if you do a start on the interactive renderer, it'll basically start an event loop, and you can sort of interact in the current style of that you're using. Here's a little bit more complicated pipeline. We're going to read some data, we're going to decimate it, we're going to smooth it, we're going to generate normals, and we're going to map it. So we create the reader, we set a file name, we create the decimator, we set some parameters. We create a smooth polydata filter. We set its input to the output of the decimator, set iterations and so on. Then we generate normals with a polydata normals filter. We map the data with that Cyber mapper and associate that with the actor. We set the color of the actor through its property, and we set its representation, possible in this case to wireframe or surface or whatever makes sense. We have a renderer, a render window, interactor again, and we start the event loop. And this is what you'll get. If you read the data in and view it, initially it's 50,000 triangles. After decimation, using this particular filter, you're down to 7,000. So that's a little bit more complicated pipeline. And I'm going to just go through a couple other quick concepts, and then I'll stop for questions. So the other thing that makes VTK really powerful is it has a whole collection, I don't know how many, probably a few dozen different types of widgets that allow interaction with your data. And they range from things like spline widgets to spheres you could use it for, say, positioning lights, contouring, contour widgets for drawing contours around things, image plane widgets for getting the planes of a 3D volume, and including oblique views, and sampling or probing pixel values at points in the data. You can generate various types of finite planes. This is great for seeding streamlines. Line widget for, in this case, seeding stream ribbons. There's things like box widgets, implicit plane widgets for transforming, cropping, cutting, clipping. And there's very specialized widgets like this checkerboard widget, which interleaves two images. If you're trying to do like registration or image compare, you can sort of create a grid and sort of side by side, cell by cell compare one to the other. Related widget is the rectilinear wipe widget, where you can control the horizontal and vertical line, move it around interactively, and compare side by side two widgets, two images. So I'm going to stop there, and I think we should look for some questions.
All right, we do have a question again. Let me
Okay.
just read that to you. It's Alexandergal, and he's asking, are there any plans to use devices like the HoloLens with VTK, or are there ways that game engines, for example, Unity, can easily communicate with VTK in both directions?
Right. So I didn't catch all that, but I think I got enough to answer it. So first of all, Pair Review and VTK support a lot of AR, VR devices. And it's constantly changing because the devices are constantly changing and they're constantly emerging and disappearing and so on. But VTK supports most, if not, well, most of the common AR, VR devices. Now, I think you also mentioned Unity, correct?
Yes.
Yeah. So we actually have integration of VTK and yes, of VTK into Unity. And if there's a question afterwards, I can provide more details. So if you want to gather up questions that I don't fully answer, I'm happy to respond back with where you can find out more information. Some of this stuff I'm not 100% on top of, so I can't provide enough at this moment, but I'm happy to get back.
Sure, that sounds good. There's no further questions at this point.
Okay, great. Thank you.
Thank you.
All right, so we're going to move into the last major section of this little course here, which is we're going to talk about image computing. And here are some pretty pictures representing some of the stuff you can do. On the left, you have, I believe, someone's reading a DICOM image, and we're looking at some grayscale intensity map. In the center, there's a volumetric rendering, probably, I'm guessing I'm not exactly sure what it is, CT scan possibly. And then we have some biological data. So there's a variety of things you can do with image data. And just to reset ourselves, I want to point out that image data is what we call things that are 1D, 2D, or 3D volumes. And it's a uniform rectilinear axis aligned data set. It has implicit geometry and topology. It's defined by an origin, its dimensions or extent, which is the same thing, and spacing. And there are other regular data sets in VTK like rectilinear grid and structured grid, but they are different in that they have explicit geometric representations while the topology is implicit. Image data benefits because of its regularity and simplicity. It can be greatly accelerated in terms of processing. I mean, I think everybody listening to this knows that. And it includes rendering too. So we'll talk about volume rendering a little bit. So we're talking about 2D and 3D volumes defined by dimensions, spacing, and an origin. And we also have this notion of VTK of extents that may or may not start at 0 and may actually include negative value, which, just to keep life interesting, is useful when you're doing certain cropping and data processing algorithms to have that flexibility. And the image processing is pretty simple. You basically have something similar to what I showed previously. You have some sort of image data coming from basically it's a mapper. You have an image actor with a property. The image actor is associated with a renderer, the renderer with a render window, and so on. And there's a special interactor style for images. There's at least one or more. And then there's a whole bunch of image processing filters like, appending components, appending two images, blending, doing difference, magnify, reslice. I would not say that the VTK's image processing system is the latest and greatest. You might want to look at something like the Insight Toolkit, ITK, which has a more sophisticated image processing pipeline. But VTK has some basics, so you can do some simple stuff, especially if you're trying to construct textures or other 2D images that you need to apply to your objects. So here's an example of how you might create image data using the very primitive VTK dataset API. This, I believe, yeah, probably not quite right, but it looks like Python, but it's not quite right. But anyway, you create images, set dimensions, set origins, set spacing. You create a data array, design unsigned car array. You set number of components, set number of values, which is the size of the volume, I by j by k. And then you insert a bunch of values, and then you set the image's point data with a set scalars command. And then you get something like what's shown on the right-hand side. And in VTK, we don't distinguish strongly between 2 and 3D images. If you're doing a 2D image, basically the dimensions in the 3D direction, the Z direction, or whatever direction is 1. So you can load in things like 2D JPEGs or DICOMs. It's not an issue. And if you have a volumetric data set, it's easy to treat the slices of the volume as images and then process and view those. And you can do that with sort of setting a display extent, which tells, it indicates to the system which slice to display. So 2 ways to visualize 3D image data. There's sort of one approach is to use an isocontouring approach. And this is more similar to what I showed you just a few minutes ago. You basically load in a volume, and then you use something like, you use some sort of contour filter. This could be marching cubes, or more likely lately, we're using Flying Edges 3D because it's incredibly much faster, and it's threaded. So it runs anywhere from, I've seen it run 500 times faster than marching cubes, depending on the size of the data. But you generate a mesh, you map it with a lookup table, use an actor property renderer and so on. And you basically render a surface. Another approach is to use volume rendering. And what you're doing there, and I'll talk about this in a second, is you're basically looking through your data as if it's translucent. And depending on the mapping function, as you move through your data, you're going to get different effects. So you use a volume mapper. And rather than using an actor, you use a volume, which has a volume property. It has lookup table, it has opacity, and some other functions you set in order to do the mapping between voxel value and RGB alpha value, renderer with cameras and lights and so on. So this is typically how one of our mappers would work, the GPU volume raycast mapper. You basically, from the eye position, you shoot rays through the pixels on the screen. They enter your volume, and as the ray propagates through the volume, it does some sort of accumulation function to basically assign a final RGB alpha to the pixels on the 2D screen. So depending on these raycast functions, you can do things like, additive. You can add values together. You can average the values as the ray passes through. You can find the maximum intensity of a voxel value, so a MIP operation. Or you can do some sort of alpha composite blending to basically get more subtle effects. And you can factor in things like gradient magnitude and other features of the data to give a very nice realistic effect. And along with these, the mapping function, you also have things which are called transfer functions. They're like lookup tables, but they're fancier. And they map the data from the volume into color and into opacity And then that's combined in the blending operation to give you different effects. So you can see same data, different transfer functions, and you can get very, very different results. Again, I'm going to point you to an application. In this case, 3D Slicer, which is it's an open source toolkit or open source application available at slicer.org. And it's a pretty fully featured medical computing, medical visualization application. It's built on top of VTK. It's also built on top of the Insight toolkit that I mentioned. And it's got a very nice architecture. You can do all sorts of plugins, and you can write your own little algorithms and plug them into the system. It's a very nice system, and I encourage you, if you want to do volume rendering and you want to do image processing and image viewing, you might want to start with this application at first before you actually start trying to use VTK. All right, so I'm going to stop there and see if there's any questions at this point.
Yes, we have another question.
Okay.
One is about shaders in VTK. So Saeed Borber, he asked, or she asked, if there's any tutorial resources about using shaders in VTK.
The answer is yes, but I need to get back to you on where best to look. And part of my confusion, and I apologize for this, is things change, and also sometimes we develop resources for some of our customers, but they're not open source because the customer doesn't want them to be. So the best thing to do is you can forward me the question. I can respond with a resource.
We will do that. Thank you so much. At this point,
Okay.
no further questions.
Okay, we're good?
We're good.
All right, just a quick segue, just to let you know that VTK does do more than scientific visualization. So what we've been looking at so far is data that has a spatio-temporal nature, and it usually corresponds to something that in worlds, let's call it world space. And so it's very easy for humans to relate to that data, because if you show somebody a rendering of a skull, almost instantaneously people understand what it is and how to interact with it and what it might be telling them. However, if you look at abstract information like tables or graphs or trees, and then you try and visualize that, in many cases, the abstraction of the visualization process is such that you need a lot of explanation to sort of describe to people what they're looking at. And that often requires a lot of interaction, so you can actually interact and build the mental models in your head. So the InfraInfo is something VTK does. It's a scope down capability. We don't do a ton of it because there's a lot of great tools out there, but it is available. And I'll just show you a couple of things it can do. There are data set structures for tables, graphs, and trees. And there's various algorithms for doing things like layout, network layout, and you can see that matrix in the upper left showing different types of layout patterns. There's capabilities for things like tree maps. This is showing, it's basically showing the hierarchy, the inheritance hierarchy of the VTK code base. And so things in the top of the tree, like object base, are the largest single rectangle, and leaf classes that way down in the inheritance tree are small little rectangles. So it's sort of cute. And you can, in this particular application, you can mouse over it and get information about what it's showing. But so tree maps are available. You can convert layouts into landscapes. with annotation. And then you can do sort of fancy stuff like hierarchical bundles and create some nice information displays. In this case, it's showing sort of the relationship of different modules in VTK. So you sort of see an inheritance across the system and dependency across the system. All right, so let's see here. Okay, this is my last slide, and then we'll take some more questions. So what are we doing now? What's new and what's happening? Well, a lot. As I mentioned earlier, the pace of development is, if anything, it's accelerating. So it's hard to say what the most interesting thing is, but these are 4 areas that I think are important. First of all, we have created a sister system called VTK.js, which is basically a JavaScript implementation of parts of VTK. It's mostly interaction, some core representations, images, and mesh and polygonal meshes. And it also has a few algorithms as well, but we're trying to stay away from a lot of algorithm implementation in VTK.js because we don't want to reproduce the algorithms, and JavaScript's not necessarily the best language for implementing algorithms, although that's debatable. But one thing we're also doing as part of this is we have a process to basically using mscripton to convert C++ into JavaScript. And then that JavaScript can be pushed down to an application client on the web, and it runs pretty well. So our strategy is for more complex algorithms. We're going to actually use WebAssembly function coupled with JavaScript to deliver algorithms through the web environment. And that's sort of an in-progress thing. It's available, but it needs a lot of work to get it to the place where it's really easy to use and robust and all that stuff. We have another sister toolkit, if you will, called VTKM, which is an activity being pursued primarily by folks in the realm of exascale computing. So these are people working on supercomputers that want to use GPUs and other accelerators to implement visualization algorithms. They have a very beautiful, absolutely gorgeous data model and data system for representing visualization data sets. It's very similar to VTK. It was very influenced by VTK, but it's also constrained because these accelerators have very strange computational requirements and constraints. So it's a language that's heavily templated, which means that when you compile it, it's complicated and it takes a long time. But if you want to run on a supercomputer, it is a very powerful and useful sister system to know about. And we have written it in such a way that it can be integrated into VTK. Basically, you can pass data down to the GPU, for example, and pull it back up into VTK. Another area related to high performance computing is we have this little subsystem called SMP tools for symmetric multiprocessing. It's an extraordinarily simple little computing algorithm, computing specification, and it really has 3 parts to it. It's got a parallel 4, it's got thread local storage, and it's got atomics. And we've actually replaced the atomics with a standard library, C++ library atomics. But anyway, it's very simple, but extremely powerful. And under the hood, it will use things like TBB or OpenMP or standard thread or serial. So I've been spending a lot of time writing algorithms threaded algorithms using SMP tools, and we're seeing performance gains on the order of anywhere from 5 to 1,000x, depending on what we're doing. So we're finding that we're making significant improvements to the speed of a lot of algorithms in VTK, which is gratifying. Because as I mentioned at the beginning, VTK was built initially as a sort of a reference implementation for algorithms, and it was quite slow. And it's nice to see it getting faster. And in some cases, we have algorithms like flying edges, which, as far as I know, are one of the fastest single pass isocontouring algorithms around. So it's good to see that. And finally, we had a question earlier about augmented reality and virtual reality. We have a lot of customers that are asking us to support different devices. For example, we're supporting Looking Glass's new hardware. And I know a lot of the other things that were mentioned earlier are supported as well. So there's a lot of activity in that front, which is fun for many people to play around with. So I'm done. Do we have any final questions?
We do. Thank you so much, first of all, for a wonderful talk. People are quite excitedly chatting away in the Discord also about the possibilities and potential, but there's also some further questions. The first question is by Tim Gerrits. He knows about the option to contribute to VTK and offer up feature implementations, but he was wondering how you decide which next feature to add or include or to work on.
Okay, okay. First of all, I just want to say it's a fantastic question. And it really, in some ways, gets to the heart of open source community, right? So VTK is an interesting system in that probably 90% of the development is done by people at Kitware. I don't know what the number actually is, but it's high. It's well over 80% for sure. So oftentimes we are driven by the people at Kitware who have customer relationships. And so priorities, quite frankly, are set by organic demand. We have customers that want something, so okay, we do it. I personally find this, I was CEO for a while, and I understand the need for business and making money and all that stuff, but I'm also a strong proponent of open source systems. So I also want to get the community involved, and I want the VTK community to become stronger, and I want to move a lot of the control and input away from Kitware into the outside community. And there are people like Bill Lorenzen, David Gobi, Andrew McLean, and others who have made huge contributions, but I would like another 4 or 5 people like that. So the question is, how do we decide? How we decide basically is a combination of organic customer pull. It's a combination of ambitious people who feel strongly about something and are willing to put in the work to code it up. And part of it too is just emerging technologies like the C++ standard is constantly evolving. So things like iterators, the standard library, and other sort of supporting structures are slowly being introduced into VTK. So in the end, it's a long community discussion and to set priority. But there's also important to remember that there's a saying that I like a lot in the open source community, which is she or he who codes wins. So people that actually code up something that's pretty great have a much stronger chance of getting that added into the system. I'll just stop there.
Yeah, that makes a lot of sense. Thank you so much. Tim also has a follow-up question to this, and it's more of a meta question. So looking back at the history of VTK, is there a point where you personally think VTK should have taken a different direction? We can keep it off the record, by the way.
Well, okay, so it depends on scale, right? So what I mean by that is like, there's some design problems at a low level in VTK, and some of them I introduced because I just screwed up. Like if you look at the design of VTK polydata, which consists of vertices, lines, polygons, and triangle strips, there's an implicit ordering of how these things need to appear. First verts, first, then lines, then polygons, then triangle strips. And that implicit order reflects back on the attribute data that goes along with the cells. Okay, so if you change the order up, like you process things in the wrong order, it screws up the results. Okay, so that's a really lousy design. I was the one that came up with it. I did it because I was in a hurry when I wrote the book. But I wish I had done it differently, and I wish I had had a single mesh representation rather than having a polydata mesh and a unstructured mesh. I think we could have done it as one and the same. So at sort of that low level of technology, there's a lot of things that I wish I had done different. I think at a higher level, I'm not sure how I would answer that. I think it's an architectural issue as how you handle complexity, whether you try to make filters do everything kitchen sink wise, or whether you sort of segregate things into specialized simple modules. I think there's a hodgepodge of that going on in VTK, and I wish that was better. And there's, I think I'll stop there.
Sure, thank you so much.
Yeah.
There's another question by Vijay Chang. He's asking, do you think that integrating with AR with VR could provide users a better experience and interactions, or would you rather provide the library for integrating with other game engines, such as Unity or Unreal?
Okay, so I'm not quite sure what exactly is the question?
The question is whether you think, I guess, I'm reading it, so I'm not sure entirely myself,
Yeah.
but I'm guessing that what he's getting at is it better to provide AR, VR functionality yourself in VTK versus integrating with an existing game engine?
Okay, yeah. I think in some cases it makes more sense to integrate with the game engine, with an external engine, because they generally have a certain way of an expectation around how data arrives and how it's dealt with. So we generally try and integrate with external packages and external systems, but that's not always possible, or the external systems are not that good. But I think I would rather integrate with an external systems.
All right, thank you. I see
Yep.
no more questions at the moment, but I would like to take the opportunity to thank you so much for your time. I think VTK is such a special toolkit in that it has sort of allowed generations of researchers to quickly prototype and make visualizations and to publish and to enable domain experts to do their work in a meaningful way. So I think this is an amazing accomplishment, and also that it's been going strong for 25 years. How many software in the open source community can say this, right? So yeah, congratulations on this also.
Yeah. Yeah.
Thank you so much also for your time.
You're welcome. You're welcome. Thanks for having me, and I hope the rest of the day goes well. Thank you.
Thank you so much. Bye.
Yeah. Take care. Bye-bye.